All right, so welcome back. Today we're going to finish up searching and sorting. And then, of course, next week will be a wrap up and a review. We'll decide what to do on Monday when we get there. But otherwise, Wednesday will be a final exam review. I'll just bring in last year's final exam and we'll do it just like we did with the midterm. Remember where we left off last time here? We had designed this linear search algorithm using a generic comparator. And yesterday you got some more practice using binary search. And so what I wanted to do now is I wanted to give you a little bit of a review of that. Remember that we've got these bank accounts. They each have an account number, a first name, a last name, and a balance. What we're going to do is we're going to sort them by the account number, and then we're going to try to find Grace Hopper's account here. Okay? So how do we call binary search? Remember that B search. Right? Remember we can only do this because we've already sorted it, right? Otherwise, we would have to rely on that linear search algorithm, and of course, then we would want to use the built-in versions, L-search or L-find. So how does B search work? Remember, it's in the standard library, so we don't need to include it. It's already included. But it takes a key. It takes a pointer to a key. Remember that. Otherwise, everything else is exactly the same as you would with quicksort. Okay? So let's go ahead and search for Grace Hopper's bank account here. And also remember that it doesn't return an index, it returns a pointer. So we're going to have to take care of that. But before we do that, let's go ahead and pass in all those other requirements. The key, the accounts, n, the size of the array, the size of each element in the array, bank account, and then the comparator that you want to use. As you observed yesterday, if you don't use the same comparator, you get completely different results. Sometimes you get invalid results because it's sorted one way, but then you search it for it using different criteria. And so you have to use the same criteria as anything else, as you use to sort with. Okay, so this will return a pointer to a bank account. So bank account. And I'm just going to call it needle, right? Why? Because I'm searching the haystack for the needle, right? Now there are two problems with this already. First of all, it returns a pointer. So is needle a pointer right now? It's just a regular old bank account. It's a regular old structure. So how do I make it into a pointer? I do that. Now, just like malloc, I also have the option of forcing it to become a bank account. Now, that'll be automatic, but if you want to be explicit about it, like we do with malloc, then you can do something like this. Remember, it returns a void pointer because it works on any array, or it works on arrays of integers, doubles, bank accounts, right? So it returns a generic void pointer to the one that you found. Not it, yes, that's it. It returns a pointer to that thing, right? I'm just forcing it explicitly to become a bank account pointer. Right? The second thing that's wrong here is this key. Remember, it takes a pointer to the key. Is key a pointer? Nope. So how do we take a regular old variable and make it into a pointer? Ampersand. Right? And this should work. Maybe. Remember that upon an unsuccessful search, it returns what? The only thing that it can return, since it's returning a pointer, is null. So let's check for null. If needle is null, then we'll print out a message. Printf unsuccessful search. Right? And let me double check. I didn't bother checking. Okay, yeah, we're good. Also remember that we are live on Piazza, so if you have questions, go ahead and please ask there. But otherwise, unsuccessful search will end the line. Otherwise, we'll go ahead and print it out. Else, it's not null, so we can go ahead and dereference it. Or I'm not even going to dereference it because it's a structure. I'll just go ahead and hand it. I don't have a print function here. I'll printf found account number whatever %d end the line and needle number. Right. Remember the definition, or I might have modified it. The definition is number, first name, last name, and balance. I do have a print accounts function here, but that's for multiple accounts. Right? I suppose I could pass it in and with a value of 1, right? That would work. It's an array of size 1. It's just a pointer to itself. So let's go ahead and run this now. And remember, it will print it. It'll sort it and then print it out. Unsuccessful search. Why? Look at my key element here. If I am searching by the number, do you see any account number with 0? Nope. So what do I need to do? I need to make sure that my key is appropriately set. So here, in this case, Grace Hopper, her account number is like that. Let's try this again. There, we found account number, and if we printed out the rest of it, of course, it would be this account right here. Now, one of the things that you observed in your lab yesterday is what if you don't follow these instructions, right? What if I sort it by number, but then I do search for it by name, right? And there's my key again, Grace Hopper. Am I going to find it? Maybe. Unsuccessful search, right? I might have gotten lucky like you did with, because that's only because there are 3 California teams in the National League, right? And so you found one of them, then you found a different one, then you found a different one just by dumb luck. And then finally, the first search, well, not finally, but the first search was the actual one that it didn't find it because you weren't searching by the correct criteria. So make sure that anytime that you are using B search, that you have to sort by the same comparator, right? So in this case, if I sort it by name, then everything will be hunky-dory again. Right? Found account number, whatever. Okay? All right. That's a good demonstration and a review. What I want to do now is wrap things up by looking at some miscellaneous things. So first of all, what happens when you've got an array of searching and sorting arrays of pointers to structures? Right? Now, this is not necessarily how I would recommend that you do your project. All right? The project means the project is going to have you opening up these this file of transactions. These are bank transactions from this account to this account. $50 has been transferred, and here's the new. Here is the balance before. Here's the balance after. There are going to be millions and millions and millions of these things. So fundamentally, you're going to have to search and sort things. Okay. One way that you can do that is like we've been covering up till now, just an array of regular old structures. But it is also possible to have an array of pointers to structures, right? Now, when we looked at structures originally, we looked at this idea where if you just have an array of structures, it's all contiguous. Here's 50 bytes for the first bank account. Here's the next 50 bytes for the next bank account, etc. It's all one big contiguous array. You could also have a pointer to all these things where this one is that over there in memory. This one is completely in a different part of memory. That one is a completely different part of memory, etc. They're scattered all over. Or you could even go with a hybrid approach where you've got an array of pointers and a contiguous array of structures, and then the pointers are pointing to various parts of that contiguous array. So everything, you get the best of both worlds, basically. If you want to swap these two, you never touch these two directly. Instead, you just by swapping them, you take the pointers to them and you make them point cross. You swap the pointers instead. Now, I'm going to. If you do want to try this as a solution for your project, great, go ahead. I'm going to show you how some pitfalls that you might end up facing. So first of all, let's go ahead and set ourselves up here. What I want is an array of pointers to structures to bank accounts. Bank account. And I'll call it P accounts. P for pointer, right? And normally that's what it would look like, right? That's what the original looks like, except that it's a static array, so we're using the that syntax right there. So, but that's what it would look like if it was just one contiguous array. I want a contiguous array of pointers, so I want a pointer to an array of pointers. Right? That's why I'm using star star. Right? Just like a character array of an array of strings, right? A two-dimensional array. Now I'll go ahead and call malloc, and cut, paste here. Malloc size of. Now, am I creating bank accounts anymore? Is that correct? And of course, I do want n of them. N is set up here to be 5, so we're good there. Oops, come on, there we go. Is that correct? No. What is this now? This is an array of pointers to bank accounts. So I want a bank account pointer, the size of a bank account pointer. Okay. A bank account could be 50 bytes or whatever it is, right? A bank account is 4, 8, 8, so 28 bytes, 50, whatever, overestimate. A pointer, however, is only probably 8 bytes. Right? Okay. Now I'm going to go ahead and initialize them all. I'm just going to reuse the ones I had from before. Int I equals 0, I is less than n, I plus plus. P accounts, the ith pointer should be equal to, I want it to equal to this one, then this one, then this one, then this one, then this one. All right? The way that I'm going to do that is accounts sub I. That won't work. In fact, if I try to compile this, I'm going to get an error. Right? Incompatible types when assigning pointers, blah, blah, blah. This is a bank account pointer. This is a regular old bank account. So how do I take a regular old bank account and get its memory address so that I can store it in a pointer? Ampersand again, right? It's going to be convenient to print these out to make sure that this operation actually worked. So let's go ahead and go over here to accounts. I'm going to go ahead and steal this print accounts and create an alternate version of it. Print accounts by pointer, right? I'm going to have to take off this const, don't worry about that. But now it's taking an array of bank account pointers. If you're wondering why I took off const, it's because the pointer array would now be const, but each element in the array that it points to would no longer be const. So I would need a complicated string of, I want a const array of pointers pointing to const bank accounts. So I don't want to get into that, right? That's too complicated. But now that I've got now that I've got an array of pointers, then account sub I, now that's a bank account pointer. So I can no longer use the dot operator. I use the arrow operator. But otherwise, everything else is exactly the same. Except for the fact that I can now change it, but not that big of a deal. Right? Make sure that I have this over in the header file as an alternative. Oops. And I will also make sure that I call it over here so that we can see that it actually, that this operation here, that this setup actually worked. And so I'll pass in P accounts and N. Right. Right. Let's see this in action. There we go. There's the printing it by account by using the pointers. And it's going to be the exact same as this one because I remember I sorted it. I sorted it before all this happened. If we want to, we can go ahead and comment this stuff out so that we get the original ordering. And you can see now that it's, oops, I still sorted it? Or no, that's the ordering from here. Joe Smith, Zelda Smith, Alan Turing, and Grace Hopper is last. Okay? All right, that has set up this thing now for an experiment. How do we go about sorting this? Well, we could go ahead and go with qsort. And qsort is now going to be, I want to sort this one. How many things are in there? N, same thing, right? But now, what about size of it? How big is each element in there? Each element is a bank account pointer. So I need that to match. Right? It's no longer a bank account. Now, what about this? Can I use the same one as before? Can I use, say, by name? Is it by name? Right. Why do we have to use a pointer for B search? I assume that you mean for the key. This is an online question. Why do we have to use a pointer for B search? Because that's how it works. It works by reference. The key has to be a pointer because it could be any type. So there is no generic non-pointer type, right? If you look at non-pointers, they have to be integers, they have to be doubles, they have to be structures, right? There's no such thing as a void type. There's only void pointers, right? Good question, though. All right. So, can I use a comparator accounts by name? Let's go ahead and take a look at that. There we go. So what does it assume that you get? It assumes that you get 2 bank account pointers. But that's not what we have over here. We have an array of pointers to to bank accounts, right? So we can't use the same comparator. In fact, if we tried, we're probably going to get a segmentation fault. Or at the very least, we're not going to get the order that we hope for. Yeah, segmentation fault. Why? Because there's a complicated diagram here, but I'm going to go ahead and think of it like this. Let's jump into here. So what is A? A is a pointer to a bank account, right? An individual element in the array you are sorting, right? It's a pointer to a bank account. That's not what we have in the array in the original the array now, right? In our array, we have pointers to bank accounts, right? So a pointer to a bank account is not the same thing as a pointer to a bank account, right? A is pointing to a bank account. In ours, A should be pointing to another pointer, which is then pointing to a bank account, right? So what we need to do is we need to create a new comparator under this assumption right here, okay? So I will go ahead and get rid of all that. And did we want to do by name? Yeah. So let's do it by name, but it'll be by pointer, right? So bank accounts by name, I'll just name it PTR because we have to have another name, right? And I will document this, this comparator is used to order an array of pointers to bank accounts, bank account structures, by the owner's last name, first name. Right. It's an array of it expects that the thing that you're trying to sort is an array of pointers, and therefore each thing in the array is a pointer, not an actual bank account. A pointer to a bank account. If you want another visualization of this, check out my book where I went to pains to draw this big diagram to illustrate what all the circuitous pointers that are going on here. I should have brought that diagram since I put so much time and effort to actually draw it. But anyway, so what we need here is to typecast it as a bank account pointer, right? Because we've got one higher level here. Now, we can't directly go to the last name. What I'm going to do is I'm going to create another const bank account. I'll call it capital A, right? And I will set that equal to X. And another one called capital B, and I'll set that equal to Y. But now be careful here. X is a bank account pointer. A is a bank account pointer. So how do I take a pointer and make it into a regular pointer? Dereference it and dereference it. And now I can use A and B all over the place here. A, B, right? And make sure that I've got this over in the header file. Remember, the only difference here is that these are bank accounts, these are pointers to bank accounts. And over here, I would have then have to use that PTR. There we go. And now this should work unless I screwed up somewhere. Hey, by name, Burke, Hopper, Smith, Joe, then Zelda, Turing. Right. So if you are going to use an array of pointers, then you have to do something like this. What about binary search? What does that look like? So let's go ahead and create. Well, we've already got our key up here. I'm going to reuse that key. In fact, here's the code from before. There's our key, right? Now, before I had to pass that in by reference. So what I'm going to have to do is I'm going to have to create a pointer to that key so that I can get the pointer to the pointer. Bank account PTR key is equal to key. And then I can pass in the memory address of the pointer. Right? And then this will be a bank account **. Right? and not accounts, but all this will be the same right here. So I could just cut and paste all of this. There we go. And I'll steal this code again, that if it's null, then unsuccessful search. Otherwise, I found account number whatever. And the way that we're going to have to do this, however, is that we're going to have to dereference it twice. Actually, no. Sorry. I think that this will work. This might not compile. No, it did. Oh, cool. Okay, you can do it like that. So, remember this kind of syntax? If it were a regular old structure, I would dereference it in parentheses and then use the dot operator. It's not a regular old structure. It is a pointer to a structure. So I dereference it once. Now it's a pointer. Now this thing is a pointer to a structure, and I can use the arrow operator. Right? So, convenient, nice, right? And you might have even been able to do something like this. Pointer, something like that. And then this would be just the key. I'm less confident, much less confident in that'll work. Yeah, no. You got to have an actual pointer there. There we go. There, turn back the clock. So I will make sure that you have all this in the notes. But again, check out the book. I don't know that Zybooks does a great job with respect to this particular topic. It was rather short. Most people got it done in, I think, less than a half hour. So it only really covers searching and sorting from a high level, not the nitty gritty of these pointers and pointers for structures and arrays of pointers to structures. Okay. All right. So sorting stability. Sorting stability. There we go. Now let's go back over here. All right, so what is stability and why is it important for sorting? So what I want to do is I want you to consider the following stability. That's spelled correctly. So consider the following values. And what I want here is, there we go, and there. Okay. So the two threes in there, I just labeled them as A and B. That's not part of the numbers. It's 3, 7, 3, and 1. Now, if I were to sort those four numbers, it would be 1, 3, 3, 7. What I did, though, is I labeled this first one as A, and I labeled the second one as B, because this 3 appeared first in the original ordering. This 3 appeared second in the original ordering. But when we go to sort them, those two that were equal, all things being equal, 3 and 3 are equal. They got put out of order, right? But if I really wanted to, I could have sorted it differently. I could have sorted it so that it would end up being the same thing, 1, 3, 3, 7, but it would end up being something like this, that the original ordering is preserved, right? An algorithm is, a sorting algorithm is stable if it never puts two otherwise equal elements out of the original order. Well, first of all, why is this important? Why would you not want an unstable sorting algorithm? So what I've got here is a demonstration using JavaScript. This is actually using the built-in sorting method in JavaScript. What I want to do is I want to sort by last name and then first name. You see that there are a bunch of students here. There's first name, last name, and UID, and of course the courses that they're enrolled in. So Starlin Castro here, he's enrolled in 3 different courses. He has the same GPA, of course, he's a sophomore, so there's a repeated information here. He's got the same email associated with each one of those courses, same NUID, etc. So let's go ahead and sort by last name, then first name. Of course, Castro would come first, then, Baez would come first, then Castro, et cetera, et cetera. Let's just go ahead and sort it, okay? So Baez, Castro, Jackson, Lake, Renteria, and Rizzo, right? And there were no Jackson. Brett came before Edwin, so it looks like it did a good job. It did its job of sorting. Let's sort it again. What happened? It changed the ordering, right? Is that what you expected? No, it was already sorted. Keep sorting it. And what happens? It always changes the relative ordering of elements that don't have the same values. So for example, here, his email associated with this is Cubs.com. His email associated with this is IowaCubs.com, right? And it changes every single time I reorder it, even though it's the same order with respect to last name, first name, right? Is that something that you would expect? Probably not. What if I wanted to sort first by year, and then let's go with GPA first, GPA descending, and then by year. Before I hit this button, what would you expect? GPAs in descending order, so the best students up here, or the best performing students up here, the worst performing students down here, right? And yeah, that's about how, Starlin Castro wouldn't be that great. Brett Jackson would not be all right, great. And Ricky Renteria was just fired, so yet again. These are all baseball folks from many years, not from many, some of them are current. But in any case, I sorted by GPA in descending order. Now, if I sort it by year, seniors, juniors, sophomores, freshmen, etc., then what would you expect? I would expect all the freshmen with the GPAs preserved. So the highest GPA freshman first, the lowest GPA freshman last. Then I would expect sophomores, highest GPA to lowest GPA. Then I would expect juniors, highest GPA to lowest. But I don't get that. I get freshmen, but 3.8. Okay, this particular example worked. There, that one it worked. That one did not work. There, sophomore 3.75, and then sophomore 2.87. Right? Oh no, that worked too. Duh. Senior. Darn it. Okay, this particular data it worked. Right? Oh well. So I wasn't able to demonstrate that, but you get the idea. If you sort it along one dimension, and then you sort it along another dimension, you expect that first dimension to be preserved. That only happens if you have a stable sorting algorithm that doesn't put two elements out of order, out of their original order. So if you want to, you do this in Excel files all the time, right? You sort, but to ensure stability, they have a selector, right? You can sort by this column, then by this column, right? And that's how you end up sorting there. But it's all because of stable sorting algorithms. So why is this important? It is often necessary, or at least preferable, to preserve the original ordering. Right? Say GPA, then by year, right? As an example. Is selection sort stable? So remember how selection sort worked. It goes through and finds the minimum, and then it puts it over here, taking this thing and moving it over here, right? So let's go with 3, 3, 1. So 2 3s right here, but A and B. 1 goes where? Here, taking this first 3, 3A, and moving it over there past this 3 right here. So no, it is not stable. Is quicksort stable? It can be. Right? Generally, you can take any sorting algorithm and make it stable by depending on the sorting algorithm, it might take a little bit bending over backwards to make it stable. But if stability is something you need and want, then you should be looking for a stable sorting algorithm to begin with. Right? And besides, you shouldn't be using selection sort almost never anyway. Okay? So that's kind of important. Another thing that's important is natural versus artificial ordering. Right? So again, let's go back to this example here. And let me go ahead, let me go ahead and refresh this and get the original just random ordering here. Now let's go ahead and sort it by year. What is the order you expect? So all the who should come first? Sophomores, freshmen, seniors, or juniors? Freshmen? Okay. Why did you say freshmen? Because they're the youngest or whatever, right? Who should come last? Seniors, okay. So who should come second? Sophomores, then juniors. All right. I agree. That's called an artificial ordering though, right? So, example. We would expect, generally, freshman, then sophomore, then junior, then senior. But a natural ordering would be what? If I just treated these as strings, that's the natural ordering, a lexicographic ordering. Which one would come first? Freshman, still, okay. We're good for now. Freshman, then what? Then junior, weird. Then what? Senior, then sophomore. I don't know why, something I picked up in grade school that whenever you're spelling a weird word like sophomore, you mispronounce it so that you remember how to spell it correctly, right? I don't know if there's a word for that, but I still do that to this day. Just like I still have to sing the ABCs in my head to get certain ordering. So those are just the skills that I never picked up of being able to understand that immediately. But anyway, that's the natural ordering, of course, would be freshman, junior, senior, and sophomore because that is alphabetic. That is lexicographic. All right. So how do we how best do we achieve this? How do we best achieve an artificial ordering of small lists of values? Well, what I could do is, in fact, let's not do juniors, seniors, whatever. Let's go ahead and come back over here and let's do a type, char type. Right? Now the type here could be, say, a gold account, a platinum account, or a premier, or I don't know. Let's go with I don't know which is better, gold or platinum. Platinum is yeah. Why? Per ounce, it's I don't know. Let's check that out. Platinum per ounce cost. What is the current cost? Per kilo, it's $29,000. Looked like. Yeah. Platinum. Oh, okay. Gold is actually more expensive than platinum. I'm not sure that those are the same measures, though. Gold is usually ounces, and platinum is what? I assume ounces. But anyway, let's go ahead. You know what? Let's make this easier. Gold, bronze, and silver. There we go. Which one is best? Gold, right? And then silver, then bronze. There, that's much easier. Right? Gold, bronze, and silver medals at the Olympics. Okay? Gold account, a silver account, and bronze account. But what would the natural ordering be? Bronze would be first, then gold, then silver. Right? So if I represented this as a string, then it would give me, so it would, as a string, it gives bronze, gold, or gold, then silver. Right? So what I would have to do is I would have to create a comparator with very, very convoluted logic, right? Let's go ahead and go with this. By type, what would it look like? It would have if A's type equals, and this is just pseudocode, this is not real code here. If it's gold and B's type, we'll list the best ones first, is equal to silver, right? Then we have to return -1 because gold comes before silver, right? Else if, and of course you would have to use strcmp to do all this stuff. I'm just doing this as a quick example of how many freaking lines of code are we going to have to write here. If the second one is gold and this is gold, then of course we will have to return 0. Right? And then we'd have to have another case where the first one is gold and then the other one is bronze, right? And then we would return -1 there, right? And so we go on and on and on. We've got 3 elements and 3 other elements possible, A and B, and so we have a total of 9 conditions. Right? We could probably cut that in half by being clever, right? But God, I don't want to do that, because what if we have to come and add yet another one? So gold, silver, bronze, and tin, or something like that, right? Then that means that I'm going to have to rewrite that entire code. So what's another way that I could do this? An enumeration. Good idea. So let's come back up here. Type def enum, and we'll call it a bank account type. I'll just go with type for now. Our bank account type. Right? And we'll put it in the order that we expect it. Gold comes first, then silver, then bronze. And then later on, if we have to add another one, just tin, right? And it preserves that ordering. So there's a type def enum, and I will represent that over here by the type, by using that instead. Now what does this comparator look like? Where were we? By type. Where are you? There we go. There it is. All right. Now what does this look like? A's type. Remember, an enumerated type at the end of the day is just an integer, right? 0, 1, 2, 3. So I could do something like this. If A's type is less than B's type, then I can go ahead and return -1. Right? Otherwise, if it's greater, I can return +1 or blah, 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 blah. But wait a second. Here's a nice little shortcut hack that is okay in this instance. Enumerated types are never going to be large, right? Enumerated types are only ever going to be, I mean, if you look at the error codes, for example, they only go up to 128 or something like that. This one certainly is only going to be 0, 1, and 2. Even if we added 10 more, it's still manageable, right? We could go ahead and take a return value of A's type minus B's type. The difference of those two things. Now, let's think about this. A's type is gold, 0. Minus B's type, which is bronze, 2. So 0 minus 2 gives us something negative, right? Yeah, gold comes before bronze. Now silver and gold, right? 1 minus 2 gives us, gold, right? 1 minus 0 gives us something positive, so it's out of order. Gold comes first. Right? This is called the difference trick, okay? And as long as you have a guarantee that it's small, the difference trick will work. The difference trick will not work in general, however, because if I have 2 billion and 2 billion, the difference there is 0. They're the same, right? But 2 billion, let's go with 2 billion and -2 billion, right? 2 billion minus -2 billion means plus 2 billion. So 4 billion, now I've got overflow at a negative value, which gives me the wrong answers. Right? So the difference trick works, but it doesn't work in general. Right? So how do we best achieve artificial ordering of small list values? Use an enumerated type. Right? Then your comparators can use the difference trick. Right? You simply compute the difference of the enumerated type's values and return the difference, right? Because 10 minus 5, or 5 minus 10 is negative, right? 10 minus 5 is positive, and 5 minus 5 is 0, right? But you cannot use the difference trick in general, because 2 billion minus negative 2 billion leads to overflow. Actually, in this, to overflow or underflow and wrong values. Okay? So avoid the difference trick in general unless you have a guarantee that it's going to be okay. And that guarantee here is simply, well, the only values that you can actually have are 1 through 3, or 1 through 2, or 1 through 3. What's even worse than tin? Aluminum. I don't know, is it? I mean, you take your cans in it, at least you get 50 cents for a pound or something like that. All right. So, as long as it's small, the difference trick will work. Okay. What else? Actually, that's it. Yeah, it didn't take as long as I thought it would. I mean, there are a couple of other things with searching and sorting, but it gets down to the nitty-gritty details and stuff like that that are not necessary. I've hit on all the major stuff, especially the stuff that is going to be useful for your project. Now, keep in mind what you have for the rest of the remaining time here. The Hack 13 basically has you do searching and sorting on your airports that you already designed. And you'll use those skills along with all the other skills that you've used this semester to get started on your project with Hack 14. Hack 14 basically has you designing your structure, has you writing code to load that structure up from a CSV file, and basic things like being able to create stuff, initialize stuff, print stuff out. You are allowed to collaborate and work with anybody that you want on Hack 14. You can take that code, even if you worked with somebody, and you can take that, go off your separate ways for the project, because with the project, no collaboration is allowed. The project is worth 100 points. That's 10% of your grade. So I would highly recommend that once you get Hack 13 done, you immediately start on Hack 14. Once you get that done, immediately start on the project. The project has you using that structure to produce a bunch of reports. A lot of fraud detection. You have to find all the accounts that result in transfers that are just under the $10,000 limit that has to be reported to the IRS for money laundering. You have to go through and apply Benford's law to see if the numbers were created fraudulently by random happenstance. You have to go through and, given two database snapshots, two very large database snapshots of 10 million transactions, you have to go through and, here's a transaction, is it missing from this other snapshot because somebody erased it from the database to hide fraud, right? You're not going to be able to do every single possibility. That, in other words, for each element over here, look at for each element over here, right? You can't do that. 10 million times 10 million, that's, what is that? Billion, trillion, 100 quadrillion? 100 quadrillion comparisons. No. That'll execute within your lifetime, but it won't execute within a week or so, or certainly not within the 5 minutes that you're allowed to run the grader. You're going to have to think of something a little bit more sophisticated. For example, what if I sorted this stuff? And I have this transaction that I'm looking for. Is it missing? If I sorted this stuff, then I could use what algorithm to quickly search for it? Binary search, right? And that will go by in a blink of an eye, just like the demonstration that we started out with, which was what? Now I forget what it was. The maliciously compliant painter, right? That leaves and has to go back and forth n squared times, and it will literally take hours to search something. Whereas if you just went through once, I think that it was replace char, right? The demonstration that I showed, or something, where for 30,000 DNA characters, if it had to go back and forth and go through it every single time you wanted to replace something and shift everything down, then that would take hours instead of instantaneous if you just went through it once. All right. All right. So be thinking about that and making sure that you've got a good start on each one of those things. 2 hacks left, 1 project left, and of course the final, which will be very much like the midterm. You'll have 24 hours to do it. Open book, open note, open computer, whatever. No collaboration on that though. You hand it in as many times as you want on that Tuesday is when it's currently scheduled, and you're good to go. Remember that is 2 hacks, a project, and a final exam, meaning that altogether that's 25% of your grade in the last week. Right? So if you haven't done so, or if you're on the bubble or something, you have 25% of your grade that you can use to improve on. But you got to get started. Not only that, but keep in mind that there are several extra credit opportunities or restoration opportunities. The extra credit, of course, is filling out the course evaluation. Please do that. And you also have the opportunity to hand in 1 hack for reconsideration. So if you missed a hack or you got 10 out of 25 or something like that, you can restore those points by handing it in again and letting me know about it. Okay? So, dealer's choice on Monday. Usually with the longer schedule, we actually cover graphical user interface programming and databases as an end cap to the next semester when we do full databases. So we might do something on that day, or I might do another demonstration to help you with your project or something like that. Okay. Have a good weekend.